Łukasz, czy możesz włączyć nagrywanie?
Już wszystko leci.
Okay, so welcome today. Our guest today is Antoine Merand from European Southern Observatory. Antoine did his PhD in Paris Observatory in France on high angular resolution observations of Cepheids. He worked as a research associate in Chara Array Interferometer in California. And then he moved to work in ESO, in the European Southern Observatory, where he is now a VLTI program scientist. And today he will tell us about interferometric observations of microlensing events. Antoine, the floor is yours.
Thank you, Prem. Thank you very much for this introduction. So thank you also, Łukasz, for inviting me and suggesting that I give this this presentation. So first, I want to give the disclaimer that the interferometric side of the title is much more my strength than the microlensing aspect. I came to microlensing a bit by accident, and I realized that, especially in Warsaw and in Poland in general, there's a very strong historical background in microlensing. So I will try to keep it to give you maybe a slightly different perspective on the topic. So gravitational lensing is when you have the deflection of the light by a chance alignment. So you have basically a source of light in the background and a foreground object that align by chance, just because everything moves in the universe. And then you have a light amplification and a light bending effect of the light of the source toward the observer. So it creates two different things. It creates an amplification, but also a deformation of the image, the apparent image of the source. So you have on the right-hand side, you have a typical object that you could see, for example, a star with a planet. And when you have the crossing, just by its proper motion, you will see the red light amplification that has this kind of typical caustic due to the presence of the planet in this case. So these events are very rare, but they are very interesting because you can measure the geometry of the system. So you can measure the distance to the lens, for example, and distance to the source in the background. But you can also measure the mass and even the mass distribution of the lens. So in the case on the right-hand side, you can see that you can detect the presence of a planet. So in that case, it would be a disturbance of the mass distribution. But if in case you have a single lens, you could, in theory, detect the mass of the lens. So microlensing is the restricted case where we talk about stellar events. So the lens can be anywhere from a planet to a star. So it could be, a fraction of a stellar mass, but it could be several stellar mass as well. Or it could be also a stellar remnant like a black hole or a white dwarf or a neutron star. They're fairly rare. They are about a few hundreds or thousands events per year, monitoring tens of millions of stars. So you have the dedicated survey. Of course, I'm sure you're very well aware of OGOL, which is based in Poland, but there are other projects like MOA or KMTNet that actually follow up objects. So you can see on the right-hand side, you have the actual passage in red of the So we are from the perspective, in this case, we're on the perspective of the source, and the lens passes in front and creates this typical two images, as well as the amplification at the bottom. So you can see from the light curve alone, and then you have to believe me on this because I'm not going to do your math, but from the light curve alone, you can easily measure some parameters, but it's almost impossible to measure the mass or the distance of the lens because they are degenerate with one another. So usually when you measure a microlens event, it's very hard to derive the mass or the distance to the lens. But why do we want the mass? And one of the main motivation is to actually get masses of objects that you cannot get the mass otherwise, such as a neutron star or black hole. If you have just a single remnant, such as a neutron star or a black hole that doesn't emit any light, either by itself or by interaction with its environment, the only way you can measure its mass is by macrolensing. There are few percent of all macrolensing events that are predicted to be neutron star of black hole. So that means since years we have been observing macrolensing, we must have in the observation, there must be a few dozens or maybe even hundreds of neutron star and black hole. The problem is that we cannot identify them. So we have the light curves, but we cannot tell if it's a black hole or just a star. Because we don't see it, and we have the degeneracy by interpreting the light curve of the microlensing. So that's why there is the whole game to actually measure masses, and one of the very interesting prospect is to get the black hole mass function. So if you think about it, black hole are the ultimate and simplest stellar remnants because of the no-hair theorem, the black hole is described only by its mass and its spin and its electric charge. But if you set aside the electric charge, which for some argument you can argue it's going to be very close to zero, the spin and the mass in particular of the black hole is very interesting, and it's a single measurement. So once you have measured the mass of a black hole, you have almost measured everything you need to know. And the black hole mass function it's a very clean and unambiguous observable, because it's really what's a result of the stellar evolution, and after you can keep interacting black holes with one another and merge them, but there is almost no more stellar physics happening. So it's a very clean in that respect observable, but it's a very complicated to measure in practice, but also it's very complicated to model, but it doesn't mean it's not worth it. So here you have a bit of a cartoon where people are trying nowadays to model the black hole mass function. So what they have to do, they have to introduce a model of the galaxy, such as how the star formation as a function of position in the galaxy, I don't know, the dynamic and so on. Plus you have to have a dynamical model afterwards to model the evolution of single star into black holes, so using stellar physics and especially supernova physics. Then you have to also say how can a binary can create a black hole via a mass exchange and stellar evolution, but also how a binary can also evolve in a binary black hole that also merge and emitting gravitational waves. So that sounds very complicated, but if you think about it from the perspective of a stellar physicist, having a one parameter object is a dream compared to a multi-parameter object such as a star and the very complex physics that it's involved. So basically what you get the end result of the stellar evolution in a very clean way, but also in a very complex way, because it combines all the history of the stellar evolution and the dynamics of the galaxy. So of course you've heard of ways of getting mass of black holes. The most popular is by far the LIGO interferometer, which uses gravitational waves to detect merging of binary black holes. So you have here in this diagram, in blue, you have the pair of black holes. So the vertical axis is the mass, and you can see the merging of black hole with the resulting black hole with its mass at the top. You also have, of course, traditionally in astrophysics, we have known about black holes by their electromagnetic emission when they're in binaries, and accrete mass very violently, and they create, in particular, X-ray emissions. And it's the same for neutron star. So basically, here you have, it's not distinctly a mass distribution, but hidden behind this is a mass distribution. And you can see the power of gravitational waves to actually detect a lot of black holes and create create this mass distribution. So what can you do with a binary black hole mass distribution? This is just one example. So on the left-hand side, you have different ways of inverting this this mass distribution. So basically, you take this diagram, you take the blue dots, especially the mass of the higher mass of the binary component, and you try to invert or infer the distribution. Since you have quite a few statistics, what people do is they try to fit analytical models. So on the left-hand side, in this recent paper from the LIGO collaboration, you have these different models, just a truncated power law or a broken power law and so on. And what you can see different things. I think the first thing you can see is that all these models, which again are based on observation, they peak around maybe 8 solar masses. So there's a peak of abundance of black holes around 8 solar masses, and then it decreases as a function of mass, and there is maybe a peak around 35 solar masses. So the peak at 9 solar masses, people try to explain it using stellar physics and stellar evolution, which I'm going to explain just after. But just also the peak at 35, it's not clear if this peak is actually present, and hopefully more statistics will confirm or infirm this peak. But it's relatively close to the maximum mass, which is thought to attain black holes via pair instability supernovae. So it's the pair instability supernovae limit is not entirely clear because it's only based on model, but it's anywhere between 30 and 50 solar masses. So it's kind of loosely related, and it could be a hint that we can actually see an effect of stellar physics. But going back to the lower limit, this is a recent work by Lieke van Son, when she tried to combine a quite simple mass transfer model, which is explained in the middle in this cartoon. So with 2 parameters, each of this underlined in colors, a small formula is a prescription for what is actually a very complex phenomenon, but there's a prescription with some parameters. And she tried to actually model the distribution of black hole, and what she got is something which is very close actually to the observed distribution. So in the top right, you can see this in gray, you have the distribution from the gravitational waves, and in pink, they have their best model. And what you have to know is actually there's a lot of different physics. And at the bottom, I just show one of the actual parameters that they can vary, which is the core fraction of the after the first mass transfer. So at the first mass transfer, you have to prescribe what is the mass of the core of the secondary compared to its envelope. And if you it's not clear what is the value, but depending on the value you have, you can get or not this sharp drop of black holes around maybe 8 solar masses, or maybe not even. You can directly connect to the neutron star formation. So whether or not there is a gap of black hole, and this is what people have been calling that there's maybe a gap or dearth of black hole between, let's say, 2.5 and 5 solar masses, it is remain to be seen, because below 2.5, we know we have a neutron star, but we don't really have, the whole game is to find a channel to actually form this relatively low mass black holes. And all the game, of course, once you show that you have or not, it constrains the model of stellar physics, just on the one I'm just showing here. So, but still, you can still have single remnants, and they are formed quite differently than this one we have been talking so far, because X-ray systems are enclosed binaries by definition, because it's the interaction of the black hole accreting from a very close companion and having a very, very strong electromagnetic emission due to the friction and the differential effects. You also have the binary black holes that leads to gravitational wave, by definition, they're also very, very close binaries because they're going to merge. So they come extremely close. But you can have, instead of physics, you can have a single neutron star or black hole via the core collapse of supernovae. So a single star can collapse into a black hole. This is a way of producing a single black hole. You can also have a black hole which is ejected after the supernova explosion. So you have a mass transfer. One of the companion or the massive, the one accreting, end up exploding as a supernova, and there is a kick that ejects the black hole. Okay, you can have a black hole in a pair already, like the ones either in a binary black hole or black hole with a star, and it's ejected by the dynamical interaction. So this is something that is modeled and is known to be possible to happen, and several models predict millions actually of single black holes in our own galaxy. And they're important to probe because they don't probe the same evolutionary path. So even though we have these very powerful techniques of gravitational waves, we also have, there is room to actually, and we have to actually detect single black hole and single neutron star because they're very important. So how do you break the mass distance degeneracy? So assuming you have a single dark lens or a single dark object, we have established the only way you can see it is by gravitational microlensing. And basically the way you break it is by measuring what is called the Einstein radius. So in the cartoon that I showed before, you have this green circle, which basically is more or less where the two images are going to form. And this is known as the Einstein radius in the formalism of microlensing. And it has the expression is given here on the left-hand side. And you can see it's basically a function of the mass and the two parallaxes of the background object and the foreground object. And in practice, is a few milliarc seconds. So if you can measure this, you can actually break you're on the way to break the mass distance degeneracy, because you need also to get some information on the distance. And it's usually done by parallactic effect. So this is an example from a few years ago where actually Spitzer and from Earth, from Ogle, a single gravitational lens was observed by two different point of view. And since you have a slightly different point of view, you can see actually different light curves, so you can infer the distance from this. Or if the event is long enough, the motion of the Earth actually is going to produce a similar effect. So you can have a wobbly effect on the light curve. It's not going just to be a Gaussian type or a Lorentzian type light curve. It's going to be a more complicated one. So if you combine these two effects, then you can derive actually the mass. So it has been done, actually, it has been done quite recently. And the way it has been done, it has not been done by measuring directly the Einstein radius, but it has been done by doing the astrometry of the system. So basically, if you think about the left-hand side, and you have these two blue images of the lens, their photocenter actually is going to move as a function of time. And this is a small effect, but it can be measured by, for example, the Hubble Space Telescope, which has an extremely stable point spread function. So you can measure this, and it has been measured recently. It took many, many years to actually measure this deflection. And you can see here is an example of the deflection as a function of time that has been modeled. And on the right-hand side, you can see in another plane, basically, which as a function of the timing of the event, so the length of the event, as a function of what's called the Einstein parallax, which is by basically the relative parallax divided by the Einstein radius. You can see those loops are actually events that have been measured. And the black dots is where basically black holes are believed to be seen. So those two, these objects, and with other, I mean, this is the most convincing object that has been analyzed by several teams, including Premec, and they have derived a mass of about 6 to 8 solar masses. So this clearly, it cannot be a star, because if it was a star of this mass, we would have seen it in photometry or spectroscopy. So just to add a few things, this was done with HST, which is an expensive telescope, and time is difficult to get. And it was done like at the 100th of the diffraction limit. So you have to measure something which is a fraction of a milliarc second. And this is extremely small compared to the diffraction limit. And also it took 7 years. So this is a very costly measurement, and you can measure only a few events. And honestly, I don't think this is how you're going to get a mass function of black holes. So of course, I think Łukasz would say, of course, the answer is Gaia. And I'm not going to go into detail with Gaia because I think it will deserve its own talk. But I want to talk to an alternate way of measuring, which is a bit the same. It's also by accessing directly by resolving actually the angular Einstein radius. So why use interferometry? So optical interferometry, as you know, is a combination of several telescopes, and it has an exquisite angular resolution. So you can go to a resolution of 0.5 milliarc second. You can do astrometry with an accuracy of 50 microarc second. So the same way HST can go way below its diffraction limit, it's the same for interferometry. If you know what you're looking at, if you can infer, if you have strong belief, you know what you're looking at, you can actually measure very precisely what you measure. And it's intrinsically a methodological technique, so it measures things. It has some limitation, it has sensitivity limitation, sky coverage, and the interpretation is not direct. So I show you here two recent examples where you can see the astrometry of exoplanets around stars. So the PDS-70 B and C, this is a very famous system. It's the only known system where planets are still forming in their transition disk. And you can see actually the exquisite astrometry on the zoom. It's very, very good astrometry. So you can actually start to infer the orbit with very few observations. And at the bottom, I also wanted to show this example because I think it's related actually in the end to black holes, because it was the observation of a system which was known to be a triple system containing a 6 or 7 solar black hole mass, 7 solar mass black hole. And actually the subject by interferometry was revealed to be a B star surrounded by a companion. So don't ask me why spectroscopy confused a triple system with a black hole with a binary with a B star. But there was this paper published quite recently, and I think I like the title because it's very blunt. It says HAR 6819 is a binary system with no black hole. So VLTI or interferometry can find black hole, but it can also deny and show that sometimes black holes are not black holes. But let's go back to microlensing. So interferometry for microlensing was already planned in the 20 years ago. So because the microlensing essentially appears as a binary, you have basically the two images of the source in the background. So in the sketch, actually the source, you don't see the source. This is where geometrically the source it is, but what you see is those two extended images which are close to the Einstein radius, and the contrast is between these two images is about 1 to a few, so it's fairly easy, and the separation is 1 milliarc second or more. And in this paper by Françoise Delplanque, she actually made some plan and some prediction about what will be observable. And you can see, I'm not going to go into the detail how they did the simulation, but basically you have this limiting magnitude column that shows the improvement of limiting magnitude with time and the number of detections. So you can see very quickly by mid-2004, we should have seen about 60 or be able to observe more than 60 per year. And of course, this is not what happened, because if it had happened, I think we would have heard about it. But to make a long story short, fringe tracking and vibration control are more difficult than we thought at ESO. So it took a lot more time to actually reach a sensitivity where we can actually observe microlensing, because something I didn't mention, but these events are rare, and they tend to be done involving faint stars, because they are much more faint star than bright stars, and faint stars are further away. So the further is the source, the more probability we have to observe an object. So everything conspired against us, and we couldn't observe. It took nearly 20 years. So this is the VLTI today. This is in Cerro Paranal in Chile. So you have this on top of Cerro Paranal, you have all these telescopes. So we have this 8-meter telescope that we can combine together, and we have the smaller 1.8-meter telescope that we can also combine interferometrically. And this is how actually we managed to do the first observation quite recently of microlensing. So this is the very first resolution of a microlensing was an event called Kojima 1. It was discovered by Kojima, who's an amateur astronomer in Japan, and he was looking for comets or over transient object, and he found actually this bright microlensing as a. This was about 10.5 in K magnitude in the infrared where the VLTI operates, and this is how we managed to observe it in 2019. So since everything is known from the system, as I explained before, because we have the light curve as shown as below, so we knew only things that we have to know is the Einstein radius and the projection angle, the orientation on sky of the contraction. And with this, we could manage to derive Einstein radius, which is about 1%. So this is a very, very good progress. And actually afterwards, it was also observed with Spitzer. So at the bottom, you can see this light curve. Actually, the black light curve is the one seen from Earth from various observatories, and the red one is the one seen from Spitzer. And as you can see, it has a different geometry, which actually is due to the fact that I explained before. The perspective from Earth is different, and it actually leads to this interesting effect that enables to measure the distance. So Zhang and Dong and collaborator in 2020, they managed to derive a mass of 0.5 solar masses and the distance to the lens to about 0.5 kiloparsec. So unfortunately, it turns out to be quite a boring object, but because of the initial mass function in the galaxy, we know that we're going to observe a lot more lenses due to low mass object than high mass object. But it shows that in principle, this observation is feasible, and this is just 1 hour observation. So in 1 hour observation, in 1 hour snapshot, we're able to derive extremely precise parameters for gravitational lensing. And the nice thing also is that 20 years after, Françoise Delplanque was also part of the team that made the first measurement after formalizing a bit how this could be done at VLTI. So there was another result very soon after, Gaia 19 BLD, which was of course a Gaia alert. And in this case, he had multi-epoch with VLTI, and also the source is resolved. So in this case, because the background source is very close to the lens, or the lens is very close to the source, we start seeing effects of the resolution of the stellar disk of the source. And in this case, the mass of the lens was derived to be a bit higher. And I think it's interesting to show also this plot that I showed from Casson et al. 21, is that they show that they can really have complementary information between the light curve and the Pioneer. So light curve is in blue and the Pioneer is in gray, and the orange gives you the Pioneer light curve, and these are the parameter, basically the relative proper motion in unit of theta e. So I think this is a very interesting, shows the complementarity between having a light curve and an interferometric observation. So this is a bit the state of the art today. We have this one single epoch observation that gave a 1% radius, Einstein radius, and a 12% mass. And we have also this multi-epoch when we have this finite source effects that shows a 0.5% precision on the Einstein radius and a 2.5% precision on the mass. But we have another object that we have been observing that is not published yet, and I'm going to show you some preliminary results. So it's also a high amplification event. This is Gaia 22 AHY. It was also observed with gravity, but this time we have 5 days close to the max magnification. So we don't have 5 consecutive days, but almost. We have the early light curve was very close to the point source point length. So the most simple case, but actually the initial VLTI analysis was very quickly, we showed that we have to have some kind of finite source, and even the finite source actually quite didn't work. And it turns out actually this is a case where the lens is a binary, and in this case actually there is a huge deformation of the of the images, which are not necessarily not easily detectable by photometry, unless you cross some special places in the plane, which are called the caustics. You don't detect them easily. So these are actually synthetic images that are they are real in the sense that they are done using the data and using a model, which is a prescription of what you can see using a microlensing event. So you can clearly see, of course, the Einstein radius, but you can see, especially on the lower left, that you have this quite asymmetrical lensing, and you can see also the finite source effect. So you can see this very thick images, and actually the source, which is the red circle, is actually at the scale really that would be on sky if we could see the source. So this is for those who are interested. These are the interferometric observer boards. So you have the UV plane, which is basically where the baselines are, the different pair of telescopes. And the middle column, you have what's called the closure phase. And on the right-hand side, you have the amplitude of the visibility of the fringes, essentially. And you can see actually the model fits very well. It's a complex model. And believe me, there is no way you have to involve a binary lens to actually solve this particular observation. So we're working still on a simultaneous fit. I showed this result already in September, but it's still ongoing because it's quite complex. I mean, people have been fitting light curve forever on gravitational lensing, but we have to combine the two, and it's quite numerically intensive, and we have to find an efficient way of doing this. But we're getting there, and we hope to have a full solution of the system, especially to show that we're able to very efficiently invert the system and get the mass very accurately. So you can clearly see there's a maturing of the data analysis, and we were lucky that the observations were done kind of in the order of simplicity. We got the first observation was by chance, a very simple system with a point source and a point lens. The second observation, we had multi-epoch, but we also have finite source and point lens. And lastly, we had more recently some multi-epoch, but with finite source, binary lens, and a time series fit, simultaneous fit. So it's moving really forward, this technique, and it shows I think it's maturing very quickly. So why I'm very optimistic also about observing microlensing with VLTI is because we have this ongoing upgrade of gravity. So gravity is the instruments that observe at the back end of the VLTI, and we have this upgrade of gravity. It's called Gravity Plus. So of course you've heard of gravity because in the context of observing the galactic center, it was key for Rainer Genzel, our colleague at Max Planck, to obtain the Nobel Prize in physics for actually the study of Sagittarius star, which is the black hole, the supermassive black hole at the center of a galaxy. But they want to go further with his team. So the upgrade is to add basically laser guide star on every telescope. So right now, only one telescope, UT4, has a laser guide star, and we're going to have also new adaptive optic system, and also have improved off-axis fringe tracking. So even if you don't really understand what it means, basically what it means is that we want to have a better sensitivity. So we have a better performance to observe exoplanet, but also go deeper in the galactic center, and also have a better sky coverage to actually observe AGNs and quasar down to cosmic noon around z equal 2.5, the redshift got 2.5. So this is the key capability for microlensing, is that we're able to pick up a star to do the fringe stabilization from 2 to 30 arc seconds, and down to K equal 2.5, but with the hope to go a bit deeper in the future. So the whole system should be on sky by 2025. We already have some promising results. So just to comment a little bit on this image you see on the right-hand side, this is an image of the galactic center done with gravity. So you have a 20 milliarc second resolution at the bottom, this white bar, and then you have various stars orbiting the galactic center. And just for an idea, this is the size of this, the square is typically the size of a pixel, the best pixel you can get on HST. So this is to imagine the confusion you have if you observe either from adaptive optics from the ground or with HST. really gravity is a machine to break the confusion and to be able to resolve all these objects. So what does it mean following up microlensing with gravity plus? So first of all, the VLTI on the UT, so the 8-meter telescope, only operates 5 to 7 nights per month, and the rest is used on the 1.8-meter telescope. So the main improvement in sensitivity will be on the UT. And this huge improvement that we expect to be at least a factor of 50, a factor of 50 will lead a factor of 50 in the number of observable microlensing. So toward the bulge, about 40% of the event will have suitable off-axis fringe tracking stars. So that means that if you take an event in the bulge, a microlensing event, we will be able to follow a little bit less than half of them. So we will be able to follow many more events with 1% angular Einstein radius down to 0.75 with maybe 0.5 milliarc second, and we can get a few percent mass as well on this object. So how many targets do we have realistically? And this is the work we have been doing with PREMEC in particular, is to take 2016 OGLE sample and to try to find targets which are suitable. So I will come back to the constraint on the Einstein radius, on the Einstein time, sorry. But really, we took really realistically what is actually observable, what we can observe, and this is a simulation of observation. So the blue bands are actually the nights where we have VLTI, and the gray are the light curve of the different events, and we assume we only catch them after they peak and so on. So we can observe basically 15 objects over a 6 months a semester, and at every month we can observe between 5 to 10 basically objects. And the most important part in this is that we selected objects. We have a long Einstein time, so the time of the crossing of the event is typically more than 50 days. And the reason why this is explained on the right hand side, we have the simulations of the galactic simulations that shows that actually black holes, which are in red in this plot, are preferably long Einstein time. And it's because of their size, because they have a larger Einstein radius in everything being equal, because of their mass, they have a longer event in the galaxy. So if you want to bias your sample towards black holes, you have to bias toward long Einstein time, which is good also because because of the way VLTI is operated, it's easier for us to actually follow up these objects. So and this from these 15 objects, we expect a handful, so maybe 2, 3, or 4, maybe even 5 black holes if the statistic is correct. And of course, you can make the argument, yeah, but these are only simulation, but that's the whole point too. If we actually measure, we start measuring statistics, we can actually say if the simulations are correct or not, and if our knowledge of the galaxy and the stellar physics is correct or not. So how does it compare actually VLTI to HST? I just wanted to make this exercise where I tried to model this event I showed you before, this MOA event where they have this black hole where they found 6 to 8 solar masses. And actually, just for fun, I took the different masses that the author they infer, and I just simulated VLTI observation. Of course, this object is not observable because it's a bit too faint actually for VLTI, even for gravity plus. But just for the sake of the argument, you can see here, even if you don't understand what these observations are, you can see that the blue, the red, and the green are very different, and they are easily distinguishable if you have the precision, which is actually the thickness of these lines, which are actually quite conservative precision for VLTI and gravity. So this is, for example, the green and the red are the two solutions preferred by Lam, Casey Lam, and the blue one is the one preferred by Kailash Sahu. And you can see actually that they are very different from the perspective of the VLTI. So if we had been able to observe with VLTI, this object would not have a mass of a precision of 15 or 20%. It will have a 1% or even less percent per precision. So it really shows, I think, that the VLTI is really a big role to play in the future. So what comes about the detectability domain, if you look where in the galaxy, if we're biased or not, this is a diagram that shows you the distance, basically, from the observer to the lens. And the vertical axis is the mass of the lens. And all this orange place is where we can observe. So I've put here the case, the source in the bulge, in the galactic bulge, so at 8.4 kiloparsec. And you can see actually that we can measure down to 2 solar masses up to 7 kiloparsecs. So basically almost all the galaxy, if there's a black hole lens, we will be able to detect it, because thanks to the angular resolution of VLTI, we can cover a huge fraction of the galaxy, essentially. And on the right-hand side, I try to put different masses for different objects. So we have this kind of black hole mass gap between 2.5 and 5 solar masses. And then above 5 solar masses, we have detected stellar black hole. So if there is a black hole in this mass gap and it happens to have a microlensing event, we will detect it. So these are really, there are also new capabilities, because I've talked about observing at high magnification. So basically when the source and the lens are very close on the sky, and this is very good because you can measure this Einstein radius, you can model the lens images, and the lens is detectable in principle, but usually it's too faint. But it's important actually to test this when we do observation, to test if we can detect the presence of blended flux due to the presence of directly the lens, because it will tell us the difference between a star and a black hole, essentially. But with improved sensitivity, we can also observe the object at much higher time, that much after the event took place. And we can still see, for example, the source and the lens, because we don't have so much amplification of the source. So the contrast between the source and the lens is easier to be detectable. So that allows to confirm dark lenses, for example. If you see an event photometrically, for example, and you want to see afterwards if you can make an image basically and see if you see the lens. And this is essentially, I took back, for example, the image of the galactic center, but imagine in this case you only have 2 objects. So this the 16.6 star is essentially the background source, and this 19.1 star is or S300, which is called for the galactic center. It would be the lens, and basically you look at the scene afterwards and you see if you can separate the 2 objects. So you can know their proper motion and so on. So it's a very powerful method. I didn't really dive into this, but it also adds to the capability to follow up microlensing. And of course, again, this is very competitive even with space telescope, because this is, for example, the pixel size of the Roman space telescope, which is going to do follow-up of microlensing. So you cannot resolve them, or you have to wait years. So instead of waiting a few weeks or a few months, maybe, you have to wait years or even decades for the two objects to be separated. So basically, my take-home message is that interferometric microlensing follow-up is maturing fast. So I've showed you we are able to determine at the percent level the Einstein radius and the mass of the lens in a few hours, compared to 2 years that are needed for HHC astrometry. We can resolve source and binary lenses. We really, it's a very method that improves parameter degeneracy. It's extremely competitive compared to astrometry if you want to do HST, Gaia with Roman, because we have this huge advantage in angular resolution. It's not competitive in terms of sensitivity, but we're getting there. To get there, we have this upgrade, which is called Gravity Plus, and it's really helping the limiting magnitude and the sky coverage. So we have already this off-axis mode called Gravity Wide, which is available since October 2022. And we will be able to access dozens or even per year with many, many single black holes detectable. And maybe before I still have a few minutes, I think I just wanted to imagine, imagining the observing lenses like this with the VLTI, with the 4 laser and with Gravity Plus. Just to show a few advertisements, if you want to use VLTI, the soonest that will happen is the VLTI summer school, the next one, which should be in June 2023 in Budapest in Hungary. So this is organized by the Concoli Observatory, and it's supported by the EII, the European Interferometry Initiative, and as well as the Optical and RadioNet Pilot Project and ESO. You can also look at what's called the European Interferometry Initiative. So they have their website, and especially they have what's called VLTI expertise centers that can help if you want to start in VLTI. They can really help you. We have the FISO program, which is also a way to finance visits. If you want to visit, if you want to visit me to work on your project, you can apply for the FISO program. And last but not least, in Krakow, in Poland, of course, in July, there will be a lunch session on the second day of the EIS annual meeting, a hands-on session basically on VLTI, to demonstrate a bit what are the capabilities and the possibilities of VLTI. But I will just leave you with my take-home message, and I will take questions from now. So I don't hear you, Premek. I don't know if I'm supposed to hear you, but I don't hear you.
We also don't hear anything.
Okay.
Okay, I think you should hear me now. Thank you again for your presentation. Do we have questions from the audience? So I will have a question. Can you show the slide about assassin source?
This one.
Yes, this one. So here you show these nice arcs. Are you actually able to measure those arcs, or just are they just simulation, or are you actually able to like measure those images?
Yes, because it's one of the parameters in the fit, and the fit really goes there. So it's one answer to this, but I think the other answer, it's really in this plot, when you see the measurement, if you see the visibility drops. And this is an indication actually of it's well connected to the thickness actually of the arcs.
Mm-hmm.
If you have infinitely thin arcs, basically the visibility will not drop like this, like it drops in this case. Okay,
so you basically measure the closure phase of visibility, and based on that you can infer the.
Yes.
Yeah. Okay.
So again, I mean, it's not a completely free image reconstruction. If you want, it's an image reconstruction, but in the domain of microlensing. So we allow the image only to be an image which makes sense in the microlensing. And we use also as initial guess for the model, we also use parameters from the light curve fit. But just maybe also to make a precision on this is that originally it's not what happened. Originally what happened is that when I looked at the data, I couldn't make sense of the data. The only thing I could fit is a ring, basically. I say, okay, maybe I see a ring, and I start fitting a ring, and it immediately works, and it works much better than trying to fit the two images like I did for Kojima one. So, and actually it was funny because I came back to Subodong, my colleague, and I said, look, it doesn't make sense. It's not, I don't understand what I'm looking at. And then he started looking very precisely at the light curve, which unfortunately, I don't think I have no, you don't see it here, but actually, if you make a zoom on the light curve, it has kind of a kink just after the maximum. It has kind of a weird kink. It's not a completely usual light curve. And then he could manage to actually infer the binarity as well of the lens.
Mm-hmm.
But I think, honestly, I think if we haven't had observed the object with interferometry, I don't think the binarity would have been caught, because the light curve is very, very close to a simple light curve.
Yes. Do we have questions on the Zoom? We don't. So I think we can.
Got a question. Maya has a question, and Pavel.
Yes, I have a question. Can you hear me?
Yes.
Okay, great. So thank you for the great talk. It's really exciting. I just wonder, because for sure gravity will also have a lot of other use cases. Do you think that all the brighter microlensing events will get the observations needed, or will it have a large competition from other cases? I know that might be a silly question, but I just wonder that.
No, that's a good question. I think it's, as you know, it's based on proposals. So basically somebody has to apply for time and says, I want to observe this many microlensing event. And this is what we have done actually with Premek and Łukasz, and then a lot of people in the community we apply for quite some time, and we're still waiting for the result. But I think it's a matter of the community, the microlensing community, to actually make a strong observing proposal to ESO and to the OPC, the Observing Program Committee, which evaluates the proposal to say, look, this is a very good science case. And it's actually a science case where you need time. Like you mentioned, you need time, you need to observe many objects, many events, because the goal is really to, in the case of the black holes, is to really to build the mass function. It's not just to detect one black hole, because I think we know black hole exists, we have detected black holes, but really the goal is to really build this mass function. So the question is like, it's a competition. So we have to get the best science case, the best proposal, and get the time to observe it. And I'm talking about, as an astronomer, not as a ESO staff, because of course ESO staff, and I cannot get access. I don't have a preferential access. I will work through the observing program committee, and it's anonymous anyway.
Thank you.
Okay, Pavel.
Okay, hi Antoine. Thank you very much for your great talk. And these results are very nice. I mean the binary lens Gaia 22AHY. And yeah, concerning this target, you have presented the visibility versus baseline plot. Yes, this one, for example. And I'm wondering what must be predicted a priori to reconstruct this visibility curve. I mean, you assume that you will see the ring and some point source or uniform disk source, or in this case, two sources and ring.
Yeah.
What must be assumed before that?
Well, you can assume essentially anything you want, but in this case, what we did is that we use a ray tracing algorithm to actually really simulate what the microlensing will look like. So basically, in this case, is a finite source, so it's a uniform disk in the background, and it has a binary lens. But what I did before, just to make sure to try to understand what we were looking at, is I model essentially a ring with an azimuthal variation, and it showed me, when it gets darker, when it gets brighter, and this is how we actually get a hint that or before confirmation that was really a binary lens.
Okay. Yeah, maybe you are aware of that, but we have a high resolution spectrum from X-Shooter for this target. And we have parameters and masses of and distance to the source, which means that we have also the distance to the lens.
Yeah, we should talk, because we just started again the process to combine, to make a simultaneous photometric fit with
would be interesting to compare the results.
Yeah, me too.
Thank you. Great.
Okay, Łukasz, do you have a question?
Yeah, just a quick question. So all the events you showed, so the Kojima, Gaia 19 BLD, then Gaia Ache, and then there's yet another one, they're all located in the disk, not the bulge. So is there any preference you would have to go for the bulge instead of the disk? So, Ogle preferentially observes the bulge, and there is way more events going on. So statistically, it's a better place to go. But the is crowding helping you, or is your enemy? And
no.
Is the disk better or not? But not better.
Well, let me see. So it's my third bullet point here, is that we need a star to actually do what we call the fringe tracking. So we need a bright object to stabilize the fringes. It's a bit like, if the equivalent of the AO guide star, if you don't have a laser. And for this, the bulge is much better. And this really boosts our sensitivity, because then if we have enough axis fringe tracking star, which is a few arc seconds away, then we can really look very, very deep for the microlensing. All the other objects I presented before, they are called on-axis fringe tracking. So we do actually the fringe stabilization on the object itself. So it needs to be fairly bright, actually, to be able to do this. But I don't know exactly why there is a bias toward the disk. I think it's just by chance, I would say.
It's much easier to observe. Only several surveys can cope with the crowding. So
yeah. I guess, yeah, okay. I guess the bias comes from this. I think there's this maybe another point. It's like there is more competition toward the bulge, because there are more objects also. So there are more VLTI observation at the time of the bulge compared to the rest.
Right. Okay. Thank you.
Okay. Thank you, Antoine. Let's thank our speaker again. And see you next week.
Thank you.